Hello everyone, welcome back. In this video, I'm going to smash all the subtitles in my way. The two kind of the first intro to where we know where from or programming back and equations. We also know or program back. Let me do that. So what is an equation? Well, equation means that the first expression equal to the second expression. But now it's not. Now it's equal. We can even do more. We can say a equal to b equal to. Then does a equal to b? Of course, that's the definition of equation. But what about the expression? If it's not your have a look at.
What I want to do is what is the value as a variable that let's start with. Say we have one. We want to know how does this like always how to work it out for yourself. Or always okay. I have so it's going to be larger value, larger value. Smaller value. You want to make it a little bit more. What is it?
Okay, everyone knows if you increase the x, the whole expression will go increase 1 and minus the number goes up. You manage bigger and bigger and bigger and bigger. Here we do the things them together.
When we're dealing with basic arithmetic, we see the concrete number there. Will be 23 plus 5. We know what these numbers are, right? We can calculate them. 28. We can say 2 times 7. We could say 3 divided by 4. In all of these cases, we know exactly what numbers we're dealing with. As we start entering into the algebraic world, and you probably have seen this a little bit already, we start dealing with the ideas of variables. And variables, there's a bunch of ways you think about them, but they're really just values in expressions where they can change. The values in those expressions can change. So for example, if I write x plus 5, this is an expression, right? This can take on some value depending on what the value of x is. If x is equal to, so if x is equal to 1, then x plus 5, our expression right over here, is going to be equal to 1, because now x is 1. It'll be 1 plus 5, so x plus 5 will be equal to 6. If x is equal to, I don't know, negative 7, then x plus 5 is going to be equal to, well, now x is negative 7. Negative 7 is going to be negative 7 plus 5 is negative 2. So notice, x here is a variable, and its value can change depending on the context. And this is in the context of an expression. You'll also see it in the context of an equation. It's actually important to realize the distinction between an expression and an equation. An expression is really just a statement of value, a statement of something I wanted. So this is an expression would be something like what we saw over here, x plus 5. The value of this expression will change depending on how this, depending on what the value of this variable is. And you could just evaluate it for different values of x. Another expression could be something like, I don't know, y plus z. Now everything is a variable. Y is 1 and z is 2 is going to be 1 plus 2. If y is 0 and z is negative 1, it's going to be 0 plus 1. These can all be evaluated, and they'll give you a value depending on the values of each of these variables that make up the expression. An equation, you're essentially setting an expression to be equal to each other. They're called equation. You're equating to this. An equation, you'll see one expression being equal to another. For example, you could say something like x plus 3 is equal to 1. And in this situation where you have an equation with only one, where you have one equation with only one unknown, you can actually figure out what x needs to be in this scenario. You might even do it in your head. What plus 3 is equal to 1? Well, you do that in your head. If I have negative 2 plus 3 is equal. So in this context, an equation is starting to constrain what value this variable can take on. But it doesn't have to necessarily constrain it as much. You could have something like x plus y plus z is equal to 5. Now you have this expression is equal to this other expression. 5 is really just an expression right over here. And there are some constraints. If someone tells you what y and z is, then you're going to get an x. If someone tells you what x and y is, and that range z is. But it depends on what the different things are. So for example, if we said y is equal to 3 and z is equal to 2, then what would be x in that situation? So y is equal to 3 and z is equal to 2, then you're going to have this the left hand expression going to be x plus 3 plus 2, going to be x plus 5, right over here, 5, x 5 is 5. And so what plus 5 is equal to 5? Well, now we're constraining that x would be equal to 0. But the important point here, one, hope you realize there's an expression and equation is that you're equating to it. The important thing to take away from here is that a variable can take on different values depending on the context of the problem. And to hit the point home, let's just evaluate a bunch of expressions when the variables have different values. So for example,
no, we don't necessarily do that. We understand the base idea of variable writing every statement real. Okay, then let's go on. Here we got a lot of different things. One step multiplication and weighting.
Let's say we have equation 7 times x. 7 is equal to 4. Now before even trying to solve, what I want to do is think a little bit about what is actually 7x equals 14. This is the exact thing as saying 7 times x, 7 times x, 7 times x. Now you might be able to do that. So 7 times 1 is that works. 7 times 2 is equal to 14. So 2 works here. So you'd immediately be able to solve it just by trying different out. Say, hey, that's going to be 2. What we're going to do in this video is think about how to solve this matter. What we're going to find is the equation more and more complicated. You're not going to be able to think about it. It's really important. One, you understand how to manipulate. Even more important, they actually represent. Literally just says 7 times x. In algebra, we don't write the time there when you write numbers next to each other or a number next to a variable. It just means that you are multiplying a short multiplication. And in general, we don't use the multiplication because it's confusing. Because x is the most common variable. And if I were to write 7 times x is equal to 14, if I write my time sign, my x will range, it might look like x times time. In general, when you're dealing with especially one of the variables x, you would use additional. You might use dot and 7 times 14, but this is still a little unusual. You have something multiplied by a variable, just write 7, literally 7. Now, understand how you have to, or how you can manipulate. Let's visualize. So 7 times x, what is that? That's saying I'm going to rewrite. I'm going to rewrite it 7 times x. So that literally means x added to itself 7 times. That's the definition of multiplication. Literally x plus x plus x plus x plus x. That's 5x plus x plus x. So that right there is literally 7x. This is 7x, right? This right here is 7x. Now, the equation tells 7x is equal to, or saying that this is equal to, or let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So literally we're saying 7x, 14 things. These are equivalent dates. Now the reason why I drew it out is so that you really understand what we're going to be divided both sides by that. So the standard step, whenever, so in general, whenever you simplify an equation down to a coefficient is just a number number multiplying variable. So some number
Sorry, I couldn't sitting here and watching him lose. Because I already understand this. So if you want to get the x, you just have to do this x to this number 14 divided by 7, and in the end you get x and inequality. This is another topic.
Most of us are familiar with equals from our earliest days. 1 plus 1 is equal to 2. Now, a lot of people might think when they see something like this, somehow equal means give me the 1 plus 1 problem, equal means give me the answer, and 1 plus 2. That's not what equal actually means. Equal is actually trying to compare quantity. When I write 1 plus 1 equals 2, that literally means that what I have on the left hand side is the exact same quantity as what I have on the right hand.
Alright, I still feel this is over complicated. As hard as I say, in the maths, a little bit unbelievable, but in the programming, it's likely. So if you want to assign the 2 to the variable b, you use 1 equals symbol. But if you want to compare two things, for example, if you want to compare a with b, you use 2 equals symbols. So that's more than here, he's introducing you the concept of inequality. Inequalities. Okay, he's introducing you the idea of inequalities. For that, we can also do it with as a Python language, programming language. For example, 2 was 2 less than 3? The answer is yes. But was 4 less than 3? The answer is no. Or we could even use a greater symbol. Was 8 greater than 7? The answer is no. Oh, sorry. The answer is 2. But was 7 greater than 5? The answer is false. I made a mistake again. Was 7 greater than, let's say, 10? The answer is false. It's kind of since you don't have to go through this, you already understand the ideas with programming language, dependent and independent.
On your math quiz, you earn 5 points for each question you answer correctly. In the table above, Q represents the number of questions you answer correctly on your math quiz, and P represents the total number of points you score on your quiz. The relationship between these two variables can be expressed by the following equation. P is equal to 5Q, where P is a point you get, and Q is a number of points correct. And you can see that in the table. If Q is 0, if you got no questions right, you get 0 points. If you got no questions right, well, 5 times 0 is going to be 0. If you get 1 question right, well, 1 times 5 is 5. You get 5 points per question. 2 questions right, 2 times 5 is 10. 2 times 5 is 10. 3 times 5 is 15. So then they ask us, which of the following they prove? Check all that apply. Let's think about it. They say the dependent variable is the number of points you score. So when you think about what's happening here, your number of points you score is being driven by how many questions you get right. It's not like somehow the teacher says you got 15 points and now you have to get exactly 3 points. The other way around. The number of questions you get right is the independent variable, and that's driving the number of points you score. So the number of points you score is the dependent variable. And typically the convention is to have the dependent variable be equal to some expression involving the independent variable. See that right here. P is dependent on what happens to you. Depending on the number of questions, you multiply by 5 and you get E. So the dependent variable is the number.
Alright, you just think about it like this. For example, here the P is the dependent variable. Why? Because it is dependent on other variables. And here the Q, this one, the Q is independent variable. Why we call it independent? Because it's in a state of dependence. So now you just think it like but anyway, it's more clear if you think the P are the dependent variable, because P depending on some other variables. Okay, those are just concepts. To be honest, in the let's say real life, you will probably never taught those ideas. Dependent is just where they are so far. So that's the equation, expression, and inequalities. Then we are going to go to the next one. Exponents, British and scientific notation. Another 3 math ideas. First one is exponents.
You already know that we can view multiplication as repeated addition. We had 2 times 3. We could literally view this as 3 2's being added together. So it would be 2 plus 2 plus 2. That's 1, 2, 3 2's, and when you add those 2's, you get it. What we're going to introduce you to in this video is the idea of repeated multiplication, a new operation that really can be viewed as repeated multiplication, and that's the operation of taking an exponent. It sounds very fancy, but we'll see with a few examples. So now let's take the idea of 2 to the third power. How we would. So 2 to the third power. So you might be tempted to say, hey, maybe this is 2 times 3 would be 6. But remember, I just said this is repeated multiplication. If I have 2 to the third power, this literally means multiplying 3 2's. So this would be equal to, not 2 plus 2 plus 2, but 2 times, and I'll use a little dot for multiplication, 2 times 2 times 2. What 2 times 2 times 2? Well, that is equal to 8. So that is equal to 8.
So that's the basic idea about the exponents. Alright, so and basically we want to read this expression. We would say 2 to the power of 3. Why we would say that the power? Because when this number, the whole number goes very high, the whole result of this expression would go to an unbelievable high level. So it somehow shows the power of it. So that's why we call it 2 to the power of. We could also do it with Python programming language. For example, if we want to get the expression value of 2 to the power of 3, we use something like this, and we will get 8. How about 2 to the power of 6, and we will get 16. And also we could get 3 to the power of 2, which would be 9. Because in the end, it's equal to 2, the multiplication of 3, or 3 times 3. This equation should be true, of course. And 2 to the power of 3, we write down 2 to the power of 3 would be equal to 2 times 2 times 2 is 3 times. And in the end, this equation should be true. So that's the idea or concept of exponents. One thing to notice that there is a special number. If you try to get the exponents from this, 0 to the power of n would still be equal to 1 to the power of n would be still equal to 1. That's two special stuff.
What I want to do in this video is think about exponents in a slightly different way that will be able to also go through a lot.
I could explain that to you, because 0 to the power of anything will literally equal to a bunch of zeros times together, and in the end, no matter how many zeros you multiply, it will always get to 0, just like what I did here. And for the 1, no matter how many 1 you multiply them together, you will always get 1. That's why. Then we come to another idea of square roots. So let's look at.
If you're watching a movie and someone is attempting to do fancy mathematics on a chalkboard, you'll almost always see a symbol that looks like this radical symbol. And this is used to the square root, and we'll see other types of roots as well. But your question is, well, what does this thing actually mean? And now that we know a little bit about exponents, we'll see that the square root symbol or the root symbol or the radical is not so hard to understand. So let's start with an example. So we know that 3 to the second power is what? 3 squared is what? Well, that's the same thing as 3 times 3. That's going to be equal to 9. But what if we went the other way around? What if we started with a 9 and we said, well, what times itself is equal to 9? We already know that answer is 3. But how could we use a symbol that tells us that? So, well, as you can imagine, that symbol is going to be the radical here. So we could write the square root of 9. And when you look at this way, you say, okay, what squared is equal to 9? And you would say, well, this is going to be equal to 3. And I want you to really look at these two equations right over here, because this is the essence of the square root symbol. If you say the square root of 9, you're saying what times itself is equal to 9? And, well, that's going to be 3. And 3 squared is equal to 9. I can do that again. I can do that many times. I can write 4 squared is equal to 16. Well, what's the square root of 16 going to be? Well, it's going to be equal to 4. Let me do it again. And actually, let me start with the square root. What is the square root of 25 going to be? Well, this is the number that times itself is going to be equal to 25, or the number where if I were to square it, I get to 25. Well, what number is that? Well, that's going to be equal to 5. Why? Because we know
this concept is a bit interesting. This concept itself is kind of interesting. But they call this one, I say, what's the square root of 16 would be, and the answer is 4. Why they call it square root? Well, when you think about it, if you draw a square, and for each of its lengths, let's say if it's 4, you know the whole area would be 4 times 4. That would be 16. What's the square root? So the square root is just 4. That's how they think about how they lamp those things because it's related to a square. What's the definition about a square? Well, it is said that 4 sets are equal. This length, this length, this length. That's the idea of square. And for this one, it's also true. If we were drawing down the square, for each side is 5. What's the area of this square? That will be 25. What's the square root of 25? Well, it's equal to 5. I hope you understand that. Sometimes people also say 5 squared would be equal to 25. But when you miss something like this, they would ask you, what's the square root of 9?
know that 5 squared is equal to.
Anyway, that's the idea of square roots. So next one, cube roots typically seems.
We wanted to figure out what x is, and if I were to square it, I already know a little bit about square roots. For example, if I were to tell you that 7 squared is equal to 49, that's equivalent to saying that 7 is equal to the square root of 49. The square root essentially unwinds taking the square of something. In fact, we could write it like this. We could write the square root of 49. So this is whatever number times itself is equal to 49. If I multiply that number times itself, if I square it, well, I'm going to get 49. And that's going to be true for any number, not just 49. If I write the square root of x, and if I were to square it, that's going to be equal to x. And that's going to be true for any x for which we can evaluate the square root, evaluate the principal root. Now, typically, and as you advance in math, you're going to see that this will change, but typically you say, okay, if I'm going to take the square root of something, x has to be non-negative. X has to be non-negative. This is going to change once we start thinking about imaginary and complex numbers. But typically, for the principal square root, we assume that whatever's under the radical, whatever's under here, is going to be non-negative. Because it's hard to square a number, at least the numbers that we know about, it's hard to square them and get a negative number. So for this thing to be defined, for it to make sense, it's typical.
Here you may ask me why he said that this x should be always positive. Well, it's simple, because if we were driving a square, the side or the road, this length should always be positive, always greater than 0. It cannot be less than 0. If it's less than 0, this square won't be x. So that's why he said that x must be greater than 0.
To say that, okay, we need to put a non-negative number in here. But anyway, the focus of this video is not on the square root. It's really just to review things so we can start thinking about the cube root. And as you can imagine, where does the whole notion of taking a square of something or a square root come from? Well, it comes from the notion of finding the area of a square. If I have a square like this, and if this side is 7, well, if it's a square, all the sides are going to be 7. And if I wanted to find the area of this, it would be 7 times 7, or 7 squared. That would be the area of it. Now, or if I were to say, well, if I have a square, and that doesn't look like a perfect square, but you get the idea, all the sides are the same length. If I have a square with area x, if the area here is x, what are the lengths of the sides going to be? Well, it's going to be square root of x. All of the sides are going to be square root of x. So it's going to be square root of x by square root of x, and this side's going to be square root of x as well, and that's going to be square root of x as well. So that's where the term square root comes from, where the square comes from. Now, what do you think cube root? Well, same idea. If I have a cube, let me do my best attempt at drawing a cube really fast. If I have a cube, and a cube, all of its dimensions have the same length, so this is a 2 by 2 by 2 cube. What's the volume over here? Well, the volume is going to be 2 times 2 times 2, which is 2 to the third power, or 2 cubed. This is 2 cubed. That's why they use the word cubed, because this would be the volume of a cube where each of its sides have length 2, and this, of course, is going to be equal to 8. But what if we went the other way around? What if we started with the cube, or what if we started with its volume? What if we started with the cube's volume, and let's say the volume here is 8 cubic units, so volume is equal to 8. And we wanted to find the lengths of the sides. So we wanted to figure out what x is, because that's x, and that's x. It's a cube, so all its dimensions have the same length. Well, there's two ways that we could express this. We could say that x times x times x, or x to the third power, is equal to 8. Or we could use the cube root symbol, which is a radical with a little 3 in the right place. Or we could write that x is equal to, it's going to look very similar to the square root. This would be the square root of 8. But to make it clear that we're talking about the cube root of 8, we would write a little 3 over there. In theory, for square root, you could put a little 2 over here, but that'd be redundant. If there's no number here, people just assume that it's the square root. But if you're
okay, so for now, everything should be quite clear. So if you use the radical symbol with a number over here, that means something. That means how many x? 3x times together would be equal to 8. What's the value of x? That means something like this. Also, for here, he's introducing you the cube root or cube root, because now this number becomes 3. Before, if it's in a square, this number would be just, and to be honest, this number could be as many as you, let's see, can be any number, doesn't have to be necessarily 2 or 3, but the idea should be very low. Let's say these two equations, first one and the second one, they are typically representing the same thing or the same cube. Anyway, I hope you understand that you don't, because in the end, you will meet a lot of questions that relate, and once you get into it, once you solve those things little by little, you would understand. I was really sure the Python also has the square function that was used. So what I'm gonna do is import the math module. Math module, it has to include a module word short name for square root. So what's the square root of 4? The answer is 2. What's the square root of 16? The answer will be 4. Then for the exponent, it has some properties for you to remember.
In this video, I want to do a bunch of involving all of these, so I can do times x to the a plus.
Okay, here he just write it down. For the x to the power of a times x to the power of b, the final answer would be x to the power of a plus b. This is the properties for components, product, or multiplication. So when you choose, for example, let's say if we got 2 to the power of 1 times 2 to the power of 2, what's the result of this expression? Well, that would be 2 to the power of 1 plus 2, which is 2 to the power of 3. And was that right? The answer would be 8. And for this one, 2 times 4 also 8. This equation was right.
And now I want to do some minus 3 powers.
Okay, it even applies for totals or division. For example, here, what's the 5 to the power of 6 divided by 5 to the power of 2 equal to 5 to the power of 6 minus the upper one minus the lower one. And this will definitely do, because in NA it's 5 power of 4. Those are just some concepts that you have to get used or remember. If you want to know why, it's also possible, because for the 5 to the power of 6, it equals to 6 numbers of 5 and divided by 2 numbers of 5. And if you cancel out the same stuff, you leave by 4 numbers of 5. That's why in the end you get 5 to the power of 4. Then we come to the negative exponents. I mean, I know it's kind of weird to have the negative involved in exponents, but how it does.
Let's take a negative number and see if we can use it.
But we can also convert it to something that we are familiar with. For example, here we got a negative exponent, negative 4. We can convert it to 1 divided by 2 to the power of 4, the positive number coming from this. So in the end, if we want to write a common rule, so 2 to the negative, 2 to the power of negative x is equal to 1 over 2 to the power of something. I just have to remember standard rate. I don't want to waste my time on it, because I want to, let's say, higher level than this. For those concepts I already familiar with, and I was good about scientific notation. So this is another idea about the number representation, because sometimes the number would be too big to represent. We just want to simplify the writing so that we would
express 0.0000 0.0000003.
So that we could represent those big numbers or smallest numbers as simple as possible. How to get the switch.
4, 5, 7 in scientific notation. Let's just remind ourselves what it means b in scientific notation. Scientific notation will be some number times some power of 10, where this number right here is going to be, let me write it this way, going to be greater than or equal to 1, and it's going to be less than 10. So over here, what we want to put here is that leading number is going to be, and in general, you're going to look for the first non-zero digit. This is a number that you're going to want to start off. The only number you're going to want to put ahead of, I guess, to the left of the decimal. So we could write 3.457. 3.457. It's going to be multiplied by 10 to something. Now let's think about what we're going to have to multiply. To go from 3.457 to this very, very small number, we have had to move the decimal from 3.457 to get to this. You have to move the decimal to the left a bunch. You have to add a bunch of zeros to the left of the 3. You have to keep moving the decimal over to the left. To do that, we're essentially making the number much, much, much smaller. We're not going to multiply it by a positive integral. We're going to multiply it times a negative integral. That the equivalent is you're kind of dividing by a positive integral. And so the best way to think about it, when you move your exponent 1 to the left, you're dividing by 10, which is equivalent to multiplying by 10 to the negative 1 power. If I have 1 times 10, clearly 1 times 10 to the negative 1, that's equal to 1 times 1 over 10, 1 over 10. 1 times, let me actually write it down to 0, to, I can add 1 times 10 to 0. Now, 1 times 10 first, 1 times 10 to 0 is 1 times 1. 1 times 10 to the negative 1 is equal to 1 over 10 is equal to 0.1. If I do 1 times 10 to the negative 2, 10 to the negative 2 is 1 over 10 squared, or 1 over 100, 0.01. What's happening? When I raise it to a negative power, I raise it to a negative 1 power, I've essentially moved the decimal from the right of 1 to the left there to there. When I raise the negative 2, I move 2 over. So how many times are we going to have to move it over to the left to get this number right? So we essentially, let's think about how many zeros. We have to move it 1 time to get in front of 3. And then we have to move it that many more times to get all of the zeros. So that we have to move it 1 time to get 3. Started here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So this is going to be 3.457 times 10 to the negative 10 power. Let's write 3.457 times 10 to the negative. So in general, what you want to do is find first non-zero number here. Remember, you want a number here that means 1 and 10 and equal to 1. Less 3.457 definitely fit that bill. It means 1 and 10. And then you just want to count the leading zeros, mean the decimal of that number, and include the number, because that tells you how many times you have to shift the decimal over to actually get this. We have to shift the 10 times to the left to get it.
Alright, that's the basic idea of scientific notation. It's just a way to simplify the expression of a very big or very small number. For some cases, it has some usage. For example, even if you want to save a very big or very small number in your computer, the computer may still get some errors. Sometimes it cannot represent a very small number. In the end, it will convert it to a scientific notation because in the end, the computer will also want to store this number into its memory or something. And in the end, if it wants to save space or save memory, it has to represent that number in orders or magnitude.
I would like to so I heard a video first. I would want to order.
Okay, he's talking about the odd. You can do this, of course, without any problem, since all those operations here for this expression is all about the multiplication. And for several of multiplication, you can always change the order from who's first, who's later. You can always change that, and that order change won't change the final result. So in the end, you'll get the same result. It's not a, for computer, it doesn't really matter for the order. It's treated in like computer here, but for human, because sometimes if you do the multiplication for the line and later you do here first, you feel simpler. Okay, that's why people do this. But one thing to mention is that the parentheses in the programming language, or I guess for the math, is also very important. Is that if you include your expression inside of a parenthesis, the one that inside this parenthesis, inside this and this would be calculated first. Then that's enough. So today in this video we have talked about the concept of equations, expressions, and inequality, and also the concept or ideas of exponents, radius, and scientific notation. So those are the basics of algebra, or the base knowledge that you have to know before you get to the algebra. Finally, we'll be able to get a higher level. So thanks for watching, and I will see you guys in next. Let's make progress every day to review our mathematics. So bye.